Welcome back, everyone. We will start our talk now, our first talk in this workshop with Professor Sherif Mourad. He is going to talk about numerical modeling and system identification of historic masonry structure in historic Cairo using dynamic investigation tests. Professor Sherif Mourad, as I said, he's he's my older brother, and he used to be the dean of our College of Engineering at Cairo University. I would like to welcome Professor Sherif Mourad, and you, Dr. Sherif, you can start now if you like.
Everyone, you can. Well, I'd like to thank Dr. Yusuf for arranging this interesting workshop and for inviting me to talk. Before of the partner is the Imperial London, led by Razuli. Team includes members of the university as well as Faculty of Archaeology, Cairo University, and Faculty of Science. In addition to called now El Umran Gaura with Dr. Ibrahim. So today I'll give a brief idea about the iconic and get into the details of the research done in a called the iconic project is an interdisciplinary project. It includes experts who do structural groundwater studies, structural health monitoring, and also conservation led by the archaeology. Proposals for reuse of empty land. This is the site management in terms of damage, investigate causes of these damage, and propose conservation and maintenance plans. This slide gives a simple idea of this task, where you see in the elevation the areas that from the structure that needs attention, colored and marked, and a picture from the structure as it is right now, and a rendering for what it should be when the restoration is complete. Task 3 is the structural assessment on a territorial scale, where you would look at the site and the different buildings in it, overall site, identify mechanisms of collapse for different buildings, and try to look at the fragility curves for these different structures. Task 4 is structural assessment for a single structure, and this is what we'll be talking about in details in this presentation. Task 3 for the structural assessment, we have identified in different buildings the local mechanisms of collapse, whether it's cracking of unreinforced masonry, bed joint sliding, vertical cracks, outward detachment of walls, pounding, deterioration of construction material. And this is a statistic listing of the different modes of failure and the number of buildings that are susceptible to it, and that's in different things. Task 5 is structural health monitoring, where we do static and dynamic monitoring systems, continuous processing and evaluation of the system, and correlation between these readings and the structural integrity of the system. Task 6 is an experimental campaign where 2 full-scale walls were tested for dry condition and 2 walls for wet condition, as well as samples for the walls under sheet. Task 6 was led by Imperial College, Professor Ahmed Razuli and Sudan Pompa. And again, to give you an idea, this is the experimental setup for the wall with the jack and the vertical loading. This is an actual picture from the lab, and this is a test of the sample of the wall where it was tested for diagonal shear. Sample of the output where the hysteresis loops for the load deformation of one of the walls. Task 7 is studying the topology and geology of the street, the Ashraf Street, looking at the hydrology and the geochemical study and groundwater modeling. And finally, the final end product with is interdisciplinary approach, looking at site management and conservation. This is an example of the output of task 7, the groundwater, and this is a 3D model of the site with proposed tile drains, and you can see the difference in levels and how the groundwater may move along the site. Okay, now back to our monument, Fatma Khatun Mausoleum. In order to start the theoretical modeling, you need a lot of insight measurements, characterization of the construction material, measurements of the geometry in order to create a 3D model. We've used dynamic identification tests to measure the frequencies and then went back to the model to update it with these values. And the final task, which is yet to be done, is the seismic assessment of the entire structure. The Fatma Khatun Mausoleum, as you see in the picture, is in Ashraf Street. It is actually missing the top dome in the current position. So right now we have only a flat roof. The dome that was there is no longer. It was built in 1284. In order to do our job, we started first with visual inspection, be familiar with the place and get the feel of the structure, the size. We used all documents for the geometry as well as site measurements. Also, the NGO Migawra had also had earlier conservation studies, which we used in our model. So in order to create our 3D model, we started by 2D sections done from AutoCAD. We started creating these sections and then extruded them into solids in order to come up with the 3D model for the entire structure. We used the program SAP 2000, and here is a picture of the structure and the 3D model. And then when we wanted to more elaborate analyses and were limited by the element library in the SAP, we switched to ANSYS and continued our analyses using the ANSYS finite element. Okay, the first step was to identify the materials of the structure. It was mainly masonry, but there were also some parts in limestone. So first we went into textbooks and we found estimations and values for compressive strength, Young's modulus, and shear modulus. The references were FEMA 356, Eurocode 6, the Italian code 617, and finally the Egyptian code for masonry. And some of the data were provided in some codes and some were missing. So this will give you an idea of the different values. For example, if you go for Young's modulus, the FEMA 550 FM, Eurocode 1000 FM, the Italian between 1500 and almost 2000 for limestone, and between 1200 and 800 for solid bricks. So as you see, there are different values for the parameters. We also did our own material testing, samples from the stone and the brick, and did our testing for the samples to get the specific gravity as well as the compressive strength of these materials. So we had 5 samples from limestone, 2 samples from brick, and 1 sample from new brick, and used these samples to get the values for the compressive strength and also for specific gravity, Young's modulus, and Poisson's. So these were the values that we got from our testing. and then we looked at the values that were in textbooks and codes and found discrepancies. So we got started with a model, and then we said we will upgrade it later. The start of the model we had assumed E300 FM mu 0.25. We assumed the foundation as hinged to the ground, and there was a big wall actually attached to the mausoleum. So in our initial modeling, we ignored that wall. This is the gravity analysis. This is a plan for the mausoleum with the corner walls clear, and the maximum stresses were computed for the foundation, at the foundation. We did also model analysis and identified the mode shapes with the different shapes. This first mode is bending, wall bending. This is a translation in the X direction, translation in the Y direction, corner bending, and torsion. And these are the values extracted from the SAP model and the ANSYS model. Of course, we're talking linear now, so the difference between the two models is negligible. The participating mass in the X direction, for the translation X, you find the largest value. In the Y direction, you find the largest in translation. And for the torsion, you find the largest value. Here are the mode shapes. This is the first mode, which is the wall bending. This is the displacement in the X direction. And this is the torsional mode. These are samples of the modes obtained from the analysis. Okay. In addition to the theoretical, we attached accelerometers, or attempted to attach accelerometers to the structure. These accelerometers are attached by placing them at one of the corners of the mausoleum. Unfortunately, the accessibility to the roof was very difficult, and we were only able to access one of the corners of the mausoleum. So we attached the accelerometers at these three locations at the same corner. Of course, we know that this would be problematic because we will not be able to identify the mode shapes because of the location, the limited location of the accelerometer. The accelerometers we used were three-dimensional, so each accelerometer provided us the acceleration in three directions, X, Y, and Z. In the signal processing, we used peak picking method and Welch estimation for the getting the peak values and peak response. This is a sample of the power frequency response versus the frequencies, different frequencies for a specific channel. And this is, again, another at a different channel. Before we actually started processing the data, we noted that there was a factory, an ice cream factory actually, right next to the structure. And it was obvious that they were using machines that had harmonic excitations, because the sound and the vibration were noticeable and visible when we were on site. The peaks that we were able to pick were contaminated by these cyclic response or cyclic values from them, from the machines next to us. So in order to improve our signal processing, we took windows with shorter time, separated the X channels from the Y channels from the Z channels, and tried to start comparing the measurements. This is an example of the mode shape that is translation. These are the 3 points that we have, the accelerometers, and these are the translations in the X direction. And this is another mode providing the translation in the Y direction. Okay. Now the moment of truth. How does these experimental frequencies compare with the numerical model? As a matter of fact, the difference was very large. The translation mode, for example, was around 2.6 from the experimental measurements and 5.7 from the finite element. The translation y direction 3.6 versus 5.8. The torsion was a little bit better. The experimental was 9.6 versus a numerical value of 8.9. So it was obvious that our finite element model needs improvements. The improvement was done by looking at two things. One of them was the soil modeling. We had information from boreholes from the soil. Our colleague, Dr. Asma Hassan, was in charge of the geotechnical part and helped us to try to come up with some values for the spring constant, vertical and horizontal spring constants that may be introduced into our model in order to improve the results. And the other improvement we looked into was the modeling stiffness of the wall. Remember, I mentioned there was a stiff wall attached to the mausoleum. So this is the model of the wall, and we applied the horizontal unit load in order to get an estimate of the stiffness for the wall. Okay, so now we of E and U. We've added more parameters, again, of the vertical spring and horizontal presenting the soil and the stiffness. So in order to come up with the best estimate of these 5 parameters, we used a nonlinear fitting technique, the regression neural network. The tools were with the MATLAB application. So we created the database, number of models. These models we use their input and output in our new value for the vertical spring and horizontal spring, as well as the wall stiffness. So each one of these models had a different value for one of these parameters, and this is how we came up with our 8,000 models that were used for the neural net. We looked at the output from the neural network and started focusing on the values of the mode. These are the original values, remember, and these are the values that we came up from the output of the neural network with the different frequencies for the mode. When applying the neural network, these are the values that we use for the updated parameters. E400 as FEM, mu 0.25, K vertical, K horizontal, and K wall. As compared to the expected parameters, 300, so we've used 400 instead of 300 for the E. The mu is the same. KV and KH are slightly lower, whereas the stiffness of the wall also was the stiffness, I'm sorry, the KV and KH that we used are higher than the original estimate, as well as the stiffness of the wall also was high. And this is how we managed to match the final model, experimental versus theoretical, as compared to the initial model, which had values that were off the measured value. Okay, finally, to look at the values provided by different codes for the Young's modulus. We've used for the stone 2200 megapascal, for the old bricks 1400, and for the new bricks 3400. The Italian code and the values in the Italian code were a bit conservative, but close to what we finally ended up doing. Of course, it's important to include soil structure interaction because it is one of the governing parameters. when we ignored the soil structure interaction at the beginning, we got values that were very far from the measured values. Typically, when we are using horizontal and vertical soil stiffness, people are used to using horizontal stiffness 10% of the vertical stiffness. From our experience, the horizontal stiffness is much higher than that. And also modeling of attached walls and wall attachments is also an important part in order to improve them. Looking at the system identification, of course, taking several measurements for during the time domain is important, because you can come up with values of the frequencies. If, for example, if you take the measurement while the cyclic machines of the ice cream factory are working, you will see the frequencies of the machines very clear. If you take measurements where these machines are off, then you can easily identify these values and exclude them from the measurement. The vertical channel also was important because it identified the values of the soil and soil stiffness, the vertical stiffness. Of course, we started with a very limited location of the sensor setup, so we're not able to capture all the mode shapes. However, we managed to work with what we had and came up with reasonable. The fitting that we used using neural network was efficient and was able to update our model successfully. Of course, our recommendations, sometimes you can do that, sometimes you cannot. Of course, avoiding harmonic excitation is important to identify the actual natural frequencies. The structure that we measured was very stiff, so the measurements of the vibration from just ambient vibration was also a big challenge. And the best measurements we were able to pick up were when heavy trucks were passing by, so that we were able to excite the structure somehow with this ambient vibration. As I mentioned, this is part of a research project. We still have a lot of work to do, of course, in the soil modeling, because if you talk with anybody who is a soil expert about using the spring constants, you will not be satisfied with that. Of course, there are much better ways to model soil. The seismic assessment of the structure, which is again another step that needs to be taken into consideration. The effect of dewatering on the structure, and finally the structural health model. I hope I was able to give you an outline of the project, and I'll be happy to answer any questions you have. Thank you very much.
Thank you, Professor Sherif Mourad. We really enjoyed your talk. And also, I noticed that you used Professor Gazetta's formula, and fortunately, Professor Gazettas is one of the colleagues of Professor Casticadellis of the same university, National Technical University of Athens. At the moment, we have something like half an hour from now to Professor Majid, second lecture, so we can open a talk now. And remember, if you need any feedback, you can use the feedback form. The feedback form, you just choose the lecture from the combo box over there, choose Professor Sherif Mourad lecture, and write any feedback. We will collect this feedback and give it to Professor Sherif Mourad, and he will reply it, and we pass it back to all of you. At the moment, we can open a discussion within the coming 10 minutes or something like that. Then we'll have a bit of tea break or something like that, and come back with Professor Majid. So anybody want to ask any question, just unmute yourself and go ahead and ask Professor Sherif.
Hello, Dr. Sherif.
Okay.
Yes.
Dr. Yusuf, hi.
Hi, Dr. Sherif. Hi, welcome.
Yeah, thank you. Yes, it's a very interesting, of course, presentation as usual. Thank you very much for sharing this with us. I was also wondering, you have, in hindsight, you looked at what you've arrived with the values you've arrived at for the stiffness of the walls, and said that the neural networks favored the Italian code rather than the other codes. Were there similar conclusions for the spring constants? Because it's a very, there are a lot of different methods to derive spring constants, especially for dynamic modeling and small strain excitations. It's not really a standardized process how to get suitable values for spring constants and such loading conditions. So were there any conclusions on how these values can be arrived at without using neural networks or without having experimental data at hand in different conditions where we're designing for the future? Would there be any recommendation on how to get suitable values for these constants?
Actually, the values that we've used were based on geotechnical reports that were done by others. And we've just started our own geotechnical investigation. And based on that investigation, we should be able to dig deeper into this area. I'm sure you agree with me that the values of the springs are usually not looked favorably from a geotechnical point of view. And this is why we were keen to do our own investigation. It should start this week, and hopefully by that time we will have more accurate values for our soil measurements, and then we can look into what you've asked, which is a better estimate for the values of the spring from actual data rather than asking the neural network to do that numerically.
I would like to comment also on this. I'm very happy actually with the presence of Dr. Sherif Mourad with us. And it's very, very good question. And I faced this question maybe from about 20 or 25 years ago. I remember I was planning to carry out a dynamic analysis of retaining walls. And it is very difficult problem, and it is very highly nonlinear problem to estimate some sort of spring value for something like that. I believe the choice made by Professor Sherif Mourad to use artificial neural network for this is very good choice. And I believe the use of the artificial neural network for such a problem is very, very, very good a choice, to be honest, because it is very highly nonlinear and it is very easy as far as you have the training data. Okay, we would like also other questions. If there is other guy would like to raise a question. Okay, Ahmed Salah raised his hand. I believe he can just unmute yourself, Dr. Ahmed, and ask you.
Yes, hello, Professor. I hope that everyone is well. It's me, Ahmed Salah, teaching assistant in Bucharest Technical University. Thank you very much, Professor. It's very interesting, especially that you used the artificial intelligence in propagating these results. It's really very interesting, especially this is the part where I'm working now. But I just have a question concerning the model analysis of answers. You made the solid model, the contact between the solid blocks. Was it adhesive material or was just fixed between the two blocks? Because I think that there is going to be totally different values for the model analysis if we change the contact surface properties, especially that in Abacus that we can do this, maybe not in ANSYS. But if we change this contact between the two blocks, or how it is performed in this model, was it totally fixed between the both blocks?
Yes, actually, I'm sure you know that if in order to do a finite element, you can either use what we call a smeared model, which is for using the entire wall as if it is one material, including the layers of the bricks as well as the mortar and everything. And this is more or less what we've used. We did not use a model that built the structure brick by brick. So this is why, of course, the model is simpler to build, and because the model analysis is a linear problem, and getting the mode shapes is more or less based on the mass and stiffness at the linear state. I don't believe it will make that much difference in getting the mode shape. However, you are 100% correct when you go to something nonlinear like predicting the seismic response. But as far as our model, we use what we call a smeared model, which is modeling the wall as an integral part, including the mortar and the brick.
Yes, thank you. That's very clear. Another quick question. If I'm going for constitutive models for the bricks themselves, do you think this, not the smeared model, but if I have adhesive model for the material or the mortar between the blocks, do you think that it will make difference?
I believe so.
First of all, I think from a model point of view, the model would be much larger, because you'll have also to model the mortar in between. So the number of elements will be huge. And as I said, if we're talking about a linear problem, which is just getting the mode shape, I don't believe it will make that much difference. But a nonlinear problem with the when you'll talk about the damage, and then the damage might be, for example, slipping along the surface of the mortar versus the damage in the brick, then these different damage scenarios will not be able to be, a smeared model will not be able to model them correctly.
Thank you, Professor Sherif.
Thank you, Professor Sherif, and thank you, Dr. Ahmed, for this nice question. I believe if you want to go for discrete model instead of a smear model, you will be able to model very small wall of this structure. It's not the full structure. It's impossible to be modeled.
Indeed.
And actually, having a structure like this by this complication is a very big challenge, to be honest. And I would like to thank you, Professor Sherif, for this nice work, to be honest. If there is any guy has any other question, he would like, he just go ahead, unmute himself and talk and ask. Remember, you can send your questions direct by writing this on the feedback form, and I will give it to Professor Sherif Mourad and he will reply it.
Dr. Yusuf, this is Dr. Ashraf Ayub.
Dr. Ashraf Ayub, welcome, Dr. Ashraf.
Welcome, Dr. Yusuf, and great presentation, Dr. Sherif. An excellent work. In fact, it's great you were able to access and install your accelerometer there, because we were having issues with accessing sites ourselves for our project. But just to clarify, a quick question. You've done some material tests. I think you've shown that in the next slide or so. Were these samples taken from the site, or how did you do these tests? Because the results seem quite different from what you got from your neural network.
Okay, the problem with taking samples from site is that you know, the archaeologists do not want to damage the structure more than it has already been damaged. So what we had to settle for was to use material that has already fallen from the structure. So this is why it might not have been very representative to the structure itself. And the other issue, as we were discussing a few minutes ago, is that we are using a smeared model, which is the brick and the mortar as a single element. So of course, also another source of opportunity.
Okay. Thank you.
Dr. Yusuf, if there are no more questions, maybe it's time to take the break before Dr. Magid's lecture.
Okay, so we will take about 20 minutes break. Then we will come back to have our nice talk with Professor Magid, Culture Heritage Preservation using Smart Structural Health Monitoring. Thank you everybody for attending, and thank you Professor Sherif Mourad for this nice talk. Thank you Dr. Ahmed, Dr. Sherif Aql, Dr. Ashraf Ayub, and see you in 20 minutes. Thank you.
Thank you. Thank you very much.